in this video, we'll be picking and practicing how to find your pivot point. Ooh, I know, scary, right? It's hard. There's a lot of choices. But if I show you these problems, once I show you these problems and explain why it's so easy, then you're not going to be scratching your head anymore. So let's go ahead and solve some problems right now. For this problem, we have a beam that weighs 700 newtons and is holding a hanging mass that weighs 500 newtons. This entire beam right here, this is the beam, weighs 700 newtons. The necessary angles to solve the problem are shown in green. So, for part A, we need to find the tension force of the cable holding up the beam. Well, currently, we don't have any sort of analysis on how to solve this. There's no information, so where do we start? There's no information for the tension of the cable, at least. So where do we start? Well, we can make a net torque. So net torque equation. This net torque equation will guide us along the way. Let's write down A. The reason why I'm writing a net torque equation is because in this net torque equation, your tension in the cable will be a variable that we can solve for. But first things first, we need to pick a pivot point where we're going to start our R vector. So remember, calculating torque is your force vector crossed with your distance vector, distance from the axis of rotation. So you can actually pick your pivot point anywhere, but there's some points that make it easier. So which point do you think will make it the easiest on this? Well, the point that is right on the wall. Well, I guess that's sort of intuitive in this problem because that's where this, beam would be rotating along. But the reason why you want to pick this is because technically, well, I'm going to allude to part B, but to part B, there's forces that the beam's experiencing on the hinge of the wall. So we don't know which direction this force goes. It could go here, it could go here, it could go here. All these different force vectors are possible. So in order to eliminate the force vector caused by the hinge on the wall, we can set the axis of rotation to be on the hinge. And in doing so, in our torque equation, no matter what the force vector is, your R vector would equal 0 since the force has no distance from the axis of rotation. The force is exactly starting on the axis of rotation. Therefore, well, F cross 0 will just be equal to 0, so we can eliminate that from our net torque equation. So if we pick this as the pivot point, that's where we'll start off our distance vectors for in our torque equation. So let's start writing off the formula for torque. Well, the formula for torque is a cross product, so it's a magnitude of force times magnitude of distance times times sine of the angle between the two vectors. So let's pick one of these things to write out first. Well, we know that we can eliminate any force vector from the wall, so we'll cancel that out. Let's draw an imaginary arrow. We can write an X over it. But we can solve for this by looking at the three forces present. So there's the force of the weight of the cable. The weight of the beam. So the weight of the beam acts on the center. Always the weight of something, especially if it's uniform in mass, acts on the center. And you can safely assume that it will be uniform in mass. Hopefully, you're not going to be doing any center of mass with integrals problems. But we can assume that the force of 700 newtons is acting down straight in the middle of this beam. Newtons. We also know that there's a hanging mass of 500 newtons, and we also know that there's a tension in the cable. So this tension is acting in, well, the direction of the cable. So let's evaluate the torque for all three of these forces: the hanging mass, the weight of the beam, and the tension. So what is the torque of this 700 newtons? Well, the 700 newton force is a magnitude of 700. The distance from the axis of rotation to this, well, since this is in the middle of the beam, we know that length L, we can represent the length of the beam as L. L divided by 2 is the distance vector here. but we don't know the angle between them. But we know that the force is going vertically down, so if we draw a force originating at our distance vector, right over here, if we were to draw a force here, this forms a 90-degree angle with the horizontal of this 30 degrees. So all we need to do is add 90 plus 30. So the angle between these two vectors is sine of 90 plus 30, which is sine of 120. But due to the fact of the nature of this force rotating this beam sort of in the clockwise position, we'll set it as negative for consistency's sake. I actually think we need more space. Hold up, let me move this. Well, for the next force, we have the mass of the 500 newtons. So this 500 newtons is also negative due to the fact it's rotating the beam in a clockwise direction. But the magnitude of this force is 500 newtons times the entire length of the beam. So this time the hanging mass is acting on the end of the beam. So the distance vector is from the axis of rotation to the beam, which is the entire length of L. And the angle between them is also sine of the angle between the distance and the force vector is also sine of 120 due to the fact that this is straight vertically down. The 500 Newton force is vertically down, so we can kind of treat the angle the same as the weight force of the beam. Now we're running out of a little bit of space, so let's Jesus Christ. Let's go to the next line. So the next line, we have the tension force now. But we don't know the magnitude of tension force, and we don't know any of the components of the tension force, so we can't solve for the tension force. So we just represent it by T. T's acting at, again, a distance of the entire length of the beam due to the fact that this cable is connected at the end of the beam. So we multiply it by L. And the sine of what angle is happening here? Well, we know that the tension force is 45 degrees from the horizontal. So if we draw this tension force, yikes, let's pick a different color. Let's pick orange. If we draw the tension force 45 degrees from the horizontal, like so, and we know that this beam is 30 degrees from the horizontal as well, we can calculate the angle. We can calculate the angle here from this force vector and your beam by subtracting 180 from 45 and from 30. So 180 minus 45 minus 30 is 105. So the angle between those, the tension force and the distance vector is 105. So now that we have this entire thing, we know that this is equal to 0. So what is this interesting property of 0? The reason why this is 0, why I wrote down 0, maybe I should have said that earlier, is because this entire system isn't moving. So that means the net torque is equal to 0. If the net torque was greater than so, then either this would be rotating upwards due to the cable strength, or it would be completely crumbling down on itself. The beam would just fold, probably rip off the wall along the way. But since the net force is 0, the net torque, sorry, we can cancel out, we can divide L by each term in this equation, because, well, 0 divided by L is still 0. So what we get left off with is an equation that looks like this. 0 is equal to sine of 120 minus 500. 500 sine of 120 plus the tension force times the sine of 105. Well, look at this problem. It's just a basic algebra problem. We have a single variable that's unsolved for. So if you want to solve for the tension force, all you need to do is isolate it. And then once you isolate it, you should end up with a tension force of 762.09 newtons. Now, this is for part A. How about for part B? Well, for part B, it's a little, I guess, not as obvious. But once I tell you this, any single torque force problem mixed together will be super, super easy. It's simply a free body diagram. It's just the free body diagram. I'm so serious. So right now, we don't know the x and y components that the hinge on the wall is experiencing. Well, x and y components of the force. I didn't type out this entire thing. But we know that this beam must have some force acting on this wall, some normal force pushing it away, and some force that's maybe keeping it upwards. So how do we solve for this? Well, we can solve for this by drawing a free body diagram. If we treat the beam just like a point, we'll have the weight of the beam, and we'll also have the weight of the hanging mass. This is 500 newtons. 500 newtons. And this is 700 newtons. This is the weight of the beam and the weight of the hanging mass. And we also have the tension force. That is 45 degrees from the horizontal. And we already determined that this tension force is equal to 762.09 newtons. So right now we have a question mark vector. There's a missing vector. And this vector is the force that's the hinge on the wall is experiencing. So I can't draw it anywhere yet because I don't know what it is. But I can take a kind of safe assumption that it's going in this direction. I'll explain why later. It's our question mark one. So what do we do here? Well, in order to find the force, all we need to do is set up a net equation, a force net equation. And this force net equation is equal to 0. The y component and the x component are all equal to 0 because we know that this thing isn't moving. So as I explained the torque, since this isn't moving, the net torque is 0. Since this isn't moving, the net forces for x and y components are 0. So what are the net forces in the y direction? Well, the y direction has a force of 700 newtons going downward, a force of 500 newtons going downward, hence the negatives. We also have a force that's going upwards, a y component of the force that's going upwards. So the y component of the force that's going upwards is 762.09 times the sine of 45. So 762.09 times the sine of 45. And the reason why I'm multiplying by the sine of 45 is so I can get the y component of this force, of this tension force right here. So if you evaluate this into your calculator, should get 538.88. Now the last thing we don't know is your question mark force. So let's represent this by n. We need to solve for the y component of the normal force. So the y component of the normal force is ny. Now it's technically not a normal force, I'd say, but we'll just call it that because it kind of represents it. So now all we need to do is solve for the n of y. So we can actually isolate n of y here, but let me just finish off the rest of this problem. So there's only two forces going the x direction. Well, there's the x component of your tension force. That's going in the negative direction. So we'll multiply it by negative cosine of 45. Well, this right here is evaluated as just equal to 538.88 newtons. Now all we have is your unknown x force. Due to the fact that both of these masses are caused by weight, they'll point straight down, so they have no x components. Now, due to the fact that they have no x components, we just have, they have no x components. I said that right the first time. Since they have no x components, our only two forces acting in the x direction is the tension x component and the normal force x component. So now all we have to do is just solve for these two. Well, once you solve for them, you should get 538.88 newtons for the x component and 661.12 for the y component. Now, for this problem, you have a board with mass 5 kilos and is laying still on a staircase. It has a length of L of 2 meters, so the entire thing is L. And the end of the plank is a distance D, 0.5 from the top of the step. So the end of the plank is a distance D from the top of the step. So this distance here from the corner of interaction from the end of the plank is a distance of 0.5 meters. Assume no friction, and the necessary angles are given in the picture. All right, first thing, Pick a pivot point and explain why. Okay, kind of more conceptual, but let's pick a pivot point here. Well, the pivot point that I would pick in this is... Oh, actually, you guys take a guess first. Okay, now you take your guess. I'm going to spoil it right here. Well, why am I picking it at the top step? Why am I not picking it at the bottom? Well, the reason why I'm not picking it at the bottom is because your bottom force has no friction. So the only force acting on the bottom part of the plank is a normal force, and we know how to calculate that. We can calculate that with an upward arrow. It goes in just one direction. But if you don't pick your pivot point here, we don't know how this plank is interacting with this corner. The vector could be going here, the vector could be going here, maybe to the left, maybe up, maybe to the right. So we will have no idea, but we can calculate the normal force on here. And we know the direction of it, therefore we know the angle that it will form with the distance vector. So, part A, boom, cha-ching, done. Let's go into part B. Well, for part B, we need to find the normal force of the plank at the lower contact point. So this guy right here. So we need to find this normal force. Well, how do you calculate that? Well, obviously in these types of problems where you pick a pivot point, you're always, like, nearly always going to be set up some net torque equation, and this net torque equation is going to be equal to 0. If it wasn't, then I don't know what your physics professor is doing, because this is exactly what I got in my class that I just took less than a month ago. But let's see. So if we set up this entire equation, what will it look like? Well, it would look like this. Well, torque net is equal to 0, and we need to write down all the forces. Well, right here is our normal force, and we don't know our normal force. So our normal force is just a variable for now. But we do know that it's pointing straight up. Since there's no friction, there is no other vector that is acting at the bottom of this book. No other force vector is acting at the bottom of this book. So the normal force is pointing straight up, therefore it makes a 90-degree angle. But the distance vector is going to be pointing like this. Well, how long is the distance vector? Well, the distance vector, since it starts off at this corner, we know that this d is equal to 0.5 meters. And we know that the entire length is equal to 2 meters. Sorry. Not 2 meters. Oh, yeah, 2 meters. I was right. Therefore, the distance between this corner and the bottom is 1.5 meters. So our normal force times 1.5, let's not use a dot, times 1.5 times the sine of the angle between them is for your cross product. But how do you find the angle between them? Well, remember, we need to put the vectors tail to tail. So if I put the distance vector tail to tail with your force vector, we can find that. Well, we know that this distance vector makes a 25-degree angle with the horizontal. So if you shift this tail to tail, it should also make a 25-degree angle with the horizontal on the top end. And we know that the normal vector makes a 90-degree angle with the floor. So we just need to add 25 plus 90. And 25 plus 90 is equal to 115. So erase this so we don't run out of space. Okay, we have our normal force, but let's set this to be negative, since the normal force moves the torque in a clockwise position. Causes rotation in the clockwise position, so it's negative. Okay, how about for the next forces? Well, since this pivot point is at the corner, we can neglect any forces going on at this corner of the staircase because the distance is equal to 0. So therefore the torque will be equal to 0. The only other force acting on this plank is the weight force. So we have the weight force. And since we didn't mention anything about this being center of mass is at the center, we can assume, or the density of the plank is different in different places, we can assume that the weight acts on the center of the plank. So the weight acts on center of the plank, but the mass of the board is 5 kilos, so we just need to multiply 5 by gravity, which is 49 newtons. So the weight force is 49 newtons. So if we write down the formula for the torque, It's 49 newtons as the magnitude of the force, and it's positive since this force technically rotates the plank in a counterclockwise direction along this pivot point, so it's going to be a positive torque. So 49 times your distance. So how do you calculate the distance? Well, using a little bit of arithmetic, you can calculate the distance. We know that the length of this plank is just 1 meter, and we know that the distance between the end and the corner is 0.5 meters. Therefore, the distance between the pivot point and the center of the plank is also 0.5 meters. So 0.5 meters is your distance. How about the angle? Well, the angle between these two vectors is calculated like so. Well, if you have your force vector drawn out somewhere else because there's less clutter, it's going to be pointing straight down. And we know that the distance vector is pointing at an angle of 25 degrees from the horizontal. So 25 degrees from the horizontal. We need to make sure that these vectors are tail to tail. So let's draw this vector tail to tail. This is our new distance vector. And we know that, again, this distance vector is also 25 degrees from the horizontal, using vertical angles as well. So if the horizontal makes a 90-degree angle with straight vertically down, then we can subtract 90 from 25 to get the angle between these two vectors. So this angle, let's not use purple, this angle right here, theta. So 90 minus 25 is just 65. So this problem just has one unresolved variable. We have a 0 and we have all the other numbers. So once you evaluate the normal force, you should get a normal force of 16 point, we need more space for that, 16.33 newtons. So your normal force is just 16.33 newtons. Okay, well, using this, we can find the force components of the upper contact point. Well, again, we can just treat the entire plank like a free body diagram. So let's treat the plank like a free body diagram. We have two forces that are acting vertically and downward. So we have our known forces, the normal force and the weight force. The normal force is just 16.33 newtons, calculated in part 3. The weight force is 49 newtons. Did I say part 3 or part B? Okay, I'll just look back on that. But now that we have these two forces, we still have an unknown force of this corner. So let's draw it. Let's draw it with a question mark. Kind of a question mark. We don't know where it's going right now. But we do know that the net force equations are equal to 0. But in this specific case, we only have net forces going in the y direction. Sorry, we only have net forces. I didn't say net force. We only have forces going in the y direction. The normal force and the weight force. So if we subtract the weight force, 49, since it's going downward, and we add the normal force, 16.33, well, we know that the final number must be some positive number. Since 49 is lower in magnitude than 16.3, and we can put, let's see, the unknown, let's see, corner force, so C. Well, we can solve for C, since it is the only unknown variable in this problem. And once you just isolate it, you should get a final force of 32.67 newtons, and this force goes straight upwards. So, as always, if you have any questions, put it down in the comment section. And if you think what I said in this video helped, consider subscribing. I would greatly appreciate it.